impressed with the ability of Breakthrough Discuss to pick the best places in the solar system. So we are here on this beautiful campus of University of California in Santa Cruz. It's a wonderful place to be here. But let's talk about the solar system in general. What can we do to explore solar system much faster and in a greater cadence? So here I will be talking about briefly, just to introduce our session number 2, talking about the new approaches of exploring solar system with the concept, Sun-Everest concept. So the Sun-Everest concept came from our work on NASA Innovative Advanced Concept, NIAC Phase 3. Thank you, NASA, for helping us to enjoy the last couple years, last 5 years were amazing working with NIAC. And Breakthrough is a partner on this program with us. So it's very natural that we are here to present the new concept that we will be discussing, the Sun-Everest concept. So thinking about NIAC, why are we here? What is my personal reason to be here? This is it. Look at this planet. It's a beautiful planet. It's beautiful, 10,000 pixels across. But will we be able to see exoplanet that close? What does it take to see an exoplanet? If we discover one, a habitable exoplanet in our neighborhood, what do we do? For example, if I take our own planet and take it to 30 parsec away, to be able to see this planet with just 1 pixel, I need to have access to a telescope of roughly 90 kilometers. Can we have that any time in the future? I don't think it's feasible. So this is why in our work, see here is Los Angeles, of course, and very conveniently 90 kilometers from JPL to Dana Point. For those of you who are familiar with LA, you understand the magnitude of the scale. And realistically, it's just about just shy of the Kármán line. So essentially, it's a large instrument. We will never be able to build it. The point is to study exoplanets, to conduct direct imaging and spectroscopy of exoplanets. We were studying solar gravitational lensing. So the sun has a significant mass, and in the solar system, this is the best object to use as a lens. And so essentially, these are the images we can have. So look on the left, you see, for example, if I take that 30 parsec exoplanet, Earth-like planet, situated 30 parsec away, and I can make the image with the solar gravitational lens with roughly 1.1 years, the 128 by 128 pixels. So this is what solar gravity lens enables. If we take a planet closer to us, let's say within roughly 3 parsec, we can talk about megapixel imaging with the solar gravitational lensing. And those images we obtained already include a contribution from the solar corona. And so this is amazing because now we can think about using solar gravitational lens for imaging. As Carl Sagan used to say, every extraordinary claim requires an extraordinary evidence. So here you go, we have the evidence. We need to go there to make those images of exoplanets. But the challenge is that it's far. It is far. If the focal region of the solar gravitational lens would be closer, then we would fly there pretty much tomorrow because it's so accessible. And with these capabilities, we can do a lot of interesting science. But here, the point is, we need to go roughly 550 astronomical units away. How do we get there? With chemical propulsion? Not possible. It takes decades. We know that Voyager 1 now travels at the distance of roughly 152 astronomical units away from the sun, and it took it over 40 years to get there. So realistically, if you think about getting there, usually you either fly fast or live long. And we prefer to do both, right? So basically, move fast and live longer. So this is what I guess this wonderful conference is all about. We are motivated to see those wonderful images, but how do we get there? We studied multiple technologies. We looked at chemical propulsion, we looked at solar thermal, we looked at nuclear, we looked at different technologies that essentially with different technology readiness. What we do, we decided to stick with solar sails because technology readiness for those components is pretty high. And I will be talking about today about technology demonstration mission that within our NIAC Phase 3 program came as a natural extension. Because essentially with the solar gravitational lens, we need to have something that is unique. If we go forward, so solar sails, the 3 technologies that enable fast transit not only within the solar system, but beyond. And those technologies are very capable today. We're talking about small sats. And of course, we're all familiar with wonderful missions like MARCO and NeoScout that will be launched soon. So essentially, those small sats, we're talking about CubeSat class missions that will be able to deliver unique science from the distances comparable to 2 astronomical units and further. Then essentially, solar sailing. In orbit, in space, we have now Icarus, LightSail, NanoSail, and soon Neo Scout will be also launched. We have multiple developments around this planet. Multiple countries are now stepping into the area of developing solar sailing capabilities to provide unique access to deep regions of the solar system and explore for multiple other uses. So here, small nuclear power is another element that actually will enable transit to those distant regions. So now you have it. Within our NIAC Phase 3 program, we decided to stick with the different, it's a different design, very different design for solar sails. We're not going with the planar sails because with planar sails it's somewhat difficult to control. We are going with a vaned approach. So we have, in this case, the company called Lagarde in 2010 come up with this SunVane concept. We're actually moving a slightly different direction. So this is the design that Explore, which is situated in Seattle, Washington, Seattle, essentially come up with this design where we have articulatable vanes. It's like sailboat. When you own a sailboat, you know that you have a wind, you have rudder, and essentially you can go against the wind. In this case, with solar sailing, we can go against the solar radiation pressure, almost. And so essentially you drop the kinetic energy, and then potential energy takes you into the inner solar system, and then we are flying very fast, doing very fast flyby around solar perihelion, and you pick up significant velocity. Here, what we have, very simplified deployment. We don't need those deployment mechanisms. It's like Chinese umbrella. You open up, very nice, made out of carbon fiber, very light element. I will show you some details of that spacecraft. So, but then it's significant power generation, especially in the inner solar system. We can talk about scalability of this approach, going to almost 400 plus area to mass ratio coefficients. So this is amazing because now you have a scalable approach that will allow you to pick up large velocities. And so here, basically the trajectory, I will talk about this a little bit later, but the main idea is that this is our technology demonstration mission for the NIAC Phase 3 program. Look at the total weight of this vehicle. It's almost 6 kilograms. And so with the 6 kilograms, we can allocate about a kilogram for a payload. So this is just the beginning, because now it's scalable. We can actually go all the way to spacecraft masses all the way to 20 kilograms, 25, 30, and essentially allocating larger payloads. So with this, what we are aiming at, we are ready to fly within about 18 months from today. Essentially, this vehicle is built, it's basically tested. I will show the pictures of the prototype of that. So the vehicle is not flight qualified, of course, but here we're talking about it's a low cost, it's very manufacturable. So essentially, we are getting all the off-the-shelf components. Those components that were flown in space already, they have significant TRL. Not everything, except everything essentially, the components, the avionics, the spacecraft components, except the vanes, except the solar sails. So we will be qualifying them before we fly. But it's rideshare compatible. You fly with rideshare, you go to high Earth orbit, you open the sails, and off you go. And essentially, we are aiming to reach the velocities here with this vehicle up to 7 astronomical units per year. What is 1 astronomical unit per year? It's about 5,000 kilometers a second. And so that gives you twice faster than Voyager went. Voyager went roughly with a velocity of 3.1 astronomical units per year. So we are aiming here at about 7, twice that. So that's a record setting. It's a nice objective. But now we're talking about this capability. It's scalable. So the idea is how can we use it? What can we do with it? This is a trajectory that we are planning to have. It's a concept trajectory. Here, what we're aiming at, essentially, we'll launch with the C30, meaning we don't need additional propulsion. We essentially, from high Earth orbit, we're opening the sails, and we're slowly going down. Essentially, within about 5 to 6 months, we're going to be around the perihelion, and then the velocity picks you up, and you go with a very large velocity, almost radially anywhere you decide to go. It's a ballistic flight after you're flying through perihelion, but now it's an amazing capability. How can we use it? So basically, how can we use it to advance science? And the point here is that, so this is what we have built. It's a 1:3 scale prototype that is now sitting in Seattle. And so we will go through a PDR in July 18th here in California. And so this is the vehicle that is essentially another pictures of that vehicle that actually is ready to be scaled in a sense. It's not yet, this one is not yet fully space qualified, but the components are already, it's use of the components that already were space qualified. So moving on, that actually brings me to the idea of sun divers. So here, imagine now that we are flying this mission, this technology demonstration mission within the next, as I said, 18 months. And so then it opens up a new paradigm in going through the solar system with a very significant speed. And the cost of that vehicle, we expect to be it's under 20 million. So the different numbers, but basically I'm giving you the higher number. So realistically, it's very affordable. When we talk about missions of that magnitude, now suddenly we are not talking about hundreds of millions. It's very affordable. Students can build missions like this in universities. And we can now start exploring solar system not once every 15 years, once every 20 years. We can start flying several missions a year with this type of approach. So what we're talking about, it's a new paradigm. When with missions like this, initially we reach technology demonstration mission capability, where we fly with 5 to 6 astronomical units a year. Then we can go in the solar system. Enceladus, Neptune, Uranus, Titan, asteroids, heliophysics, a lot of interesting applications. With this, that opens up a very new paradigm. For me personally, I'm interested to develop those technologies because then I will get to the solar gravitational lens within my lifetime. And essentially, we will be able to see those planets. I have a personal goal. By the time I'm 100 years old, I want to see that exoplanet. So that's basically, I'm on a mission. That's my personal motivation. We need to do this. And so basically, if you go forward, what is here, this concept breaks paradigm that is established in planetary physics. That's what we hope to do here. So all areas of space physics are opened. We're talking about astrophysics, planetary, and we're talking about heliophysics especially, because with heliophysics it's the most, I guess it's in a sense low-hanging fruit, because we are here within 1 astronomical units away from the sun. No new technology development is needed because all the technology that we have is already space qualified. Essentially, with this vehicle, we can form a trajectory that will be totally a polar trajectory. Imagine forming such a trajectory with chemical propulsion. Not possible with the costs that we're talking about. And so realistically, what it opens up, we can study the sun, we can go all the way to study heliosphere with this vehicle. And once the technology is developed, so what we will be limited with is, of course, the power and communication, traditional limits for any deep space mission. But there are some wonderful ideas that exist in this audience, and we have discussed them yesterday. How can we do that? And essentially, within our program, we know how to address those immediate missions that will go all the way to maybe 40 and 60 astronomical units away. So basically, that's something that can be done now. And this is a list of interesting scientific objectives that we can essentially address with this type of a mission. So, but again, the limits here. Let me go through those limits that are on the right of this chart. First of all, of course, the spacecraft bus. It is very small, it is very compact. Realistically, what we're talking about, we can use the sail for like multi-purpose. So we can put photovoltaic elements on the sail and essentially use those sails to actually to derive energy from the sun, especially when you're within 5 astronomical units. You essentially can use the sail to generate power. And then, in addition, you can form a parabola with the sail and use that parabola for microwave communication. So here you go. You have addressed power and communication. So within 5 astronomical units, you can do that. So further away, we will need different technologies. But now, with what we have, it's already quite attractive. Now we're talking about mission types, because we are going very fast. So flyby missions. So essentially, we're talking about fast flybys, impactors. We're talking about swarms of missions, because swarms of those spacecraft, not only one, but several spacecraft, that opens up a very new paradigm of thinking. What can you do? Differential measurements, going to study gravity. For example, you can fly sub-satellite in an asteroid and see the debris that would be ejected after that spacecraft collides with the asteroid. Potentially, there are lots of interesting applications. And so here, instruments will be small. And so with this, essentially, opens up a very interesting opportunity, because we will develop those instruments, and most of those instruments are already available. So basically, especially for the inner solar system. The point here, we will discuss in this session the science and technology that enables the next step. So we will fly this TDM soon, and then how do we explore the solar system with this concept? Because as you see, not only the cost, but the opportunity, but the capability essentially that system has changes everything that we are familiar with in terms of exploring solar system. And so this session will discuss different science applications, technologies that actually will move us even further. And so within the next 20 years, I do expect that this approach has the potential to change the way we do this, science in the solar system.
Thank you so much.